Hi, I'm José Antonio Villagran, and in this small video I'm going to explain how to fit the response of a given process to a first-order model with delay. So the first thing that we should know is that this kind of response is very common in the industry, and that's why these first-order models are also known as the plant or process model. Let's imagine the suspension of a car. To simplify the model, we are going to need to consider a spring, a shock absorber, and the mass that also will be the mass of the car. From the system like this one, we will expect a response like this, where t represents the movement of the car, and the t in the x-axis represents the time. Well, what we will expect with suspension is to remove the movement of the car on the desired movement and to find equilibrium. Well, here we have a plot that represents the response from a first-order model, and also we have two equations that describes the behavior of this plot. Well, this behavior or this response comes from an ordinary differential equation of first order that are transformed in the transfer function using the Laplace transform, and then these transfer functions are solved using the inverse Laplace transform in the response g as a function of time, shown in yellow. Well, this response and this transfer function depends on two parameters, the parameter k and t. K represents the gain and t the time constant. So if we know these parameters, we could represent the behavior of the first order model. So in order to fit this model, we need to calculate these parameters. The first step is to consider the limit at time goes to infinity of the response, and what we are going to find is that the term in purple is cancelled, because as time goes to infinity, this exponential decay becomes 0. And we end with this expression and in green that shows that the limit at times go to infinity of g of t is equal to ufk, where uf is the input variable, or well, the input value of the system, and k is the gain. So if we know the input value, we could know the gain of the system. The next step is to evaluate the function when time is equal to the t parameter. Substituting the t in the equation at the beginning with the t parameter, we found that t divided by t is equal to 1. So the expression is simplified as ufk multiplied by 1 minus e to the power of minus 1. This term, 1 minus e to the power of minus 1, it's approximately equal to the 63.31%. And what we could conclude is at t equals to a time equal to the t constant, the system will reach the 63.31% of its final value. If we measure the behavior of the system and we generate a plot of the one shown maybe from an oscilloscope, we can't calculate the value from the constant k and the constant t shown earlier. The constant k are calculated considering a long period of time where the system reached equilibrium. We measure that equilibrium and we solve for k if we know the uf parameter. And for the time constant t, we measure when the system reaches the 63.31% of its final value, and we measure the time where it reaches that percentage in order to find the t constant. Good news, we finally have all the parameters to describe the first order model. Now let's move through the first order model with a delay time. As you can see in this graph, as well as the last example, we have represented the response for a first order model, now with a delay time. Here we have this delay time measured and represented by the constant tau. And this graph looks really similar to the one shown earlier, and they are only moved to the right by this tau distance. Well as the last exercise, this comes from an ordinary differential equation that is also transformed with Laplace transform in the transfer function shown in blue, and then solved using inverse Laplace transforms to the response shown in yellow. The first step again is to calculate the limit as time goes to infinity, as well as the last example. And what we found is that the limit as time goes to infinity of the function g of t, of the response, is equal to UFK as well as the lag sample, and it is because we are also considering a first order model, and what the delay do is only to move to the right a certain amount of time tau the function, so the equilibrium will not be affected at times go to infinity. The next step is to evaluate the function, the response, at times equal tau plus the t parameter, and something very similar to the example shown earlier when we evaluate the response as time equals tau, is that the power of the exponent becomes -1, and as we know our example for a first order model without delay, this that 1 minus e to the power of -1 is equal to 63.32%, and well, J evaluated at time equals tau plus the t parameter will be almost equal to 63.32% of the final value UFK. Finally, because we evaluate the function, the response in the time equals tau plus the t parameter, and where here we have two parameters that we want to calculate, we need to generate another equation in order to have two equations and two variables to solve it with the system of the equation 2/2. And well, we know that the response evaluated in tau plus the t parameter divided by 3 is equal to the 28.3% of the final response UFK, and with that parameters we can solve it a system of equation in the next slide. Finally, we measure the values shown earlier, and we find this system of equation. Here we defined the inverse function of the response, t of j in that case, and if we evaluate t in the 63.32% of the final value, will be equal to tau plus t parameter, and if we evaluate the function t of j in 28.3% of the final value, it will be equal to tau plus t divided by 3. We solve this system of equation and we could find finally the response we were waiting for. Adjusting a system with a delay time is very common in the cases where the response of the actual system is much smoother at the beginning, and we have not an initial exponential increase. So we could move the complete graph or the complete response a certain amount of time in order to simplify a little bit problem, and to start the response a little bit late in order to have a complete behavior, a real or more realistic behavior with that smoother graph. That's all for today's lessons. Thanks for all.